Now let's talk about some of the key characteristics of an image sensor. We'll start with resolution, which is the number of pixels you have in the image. You can see what's happened here. Around the mid-1990s, we were very low in resolution because this technology was just being developed. And a typical image, digital image, would be something like 640 by 480 pixels, less than a megapixel. In fact, a megapixel, I remember, was considered to be a major achievement. Then that happened somewhere around here, 1998 or so. And the second problem that these chips were facing back then was they were consuming more power than we would like. And so they were drawing on the power of the device they were sitting on, or the batteries would have to be changed very frequently. And you know that in the case of a phone, say, for instance, power is really a very precious commodity. So with time, these chips got more and more sophisticated, more and more low-powered, higher in quality. And today we have very high-resolution chips. And it's easy to capture a 15 megapixel, 20 megapixel image. And this, by the way, is in 2013 that I'm showing you right here. Today you can get a 50 megapixel image with ease. More resolution than we perhaps need for most applications. That's where we are at the moment. And now let's talk about noise. What is noise? Noise is unwanted modification of a signal during the capture of the signal, or the conversion of the signal, or the transmission of the signal, the processing of the signal, or even the storage of the signal. At these various points in the pipeline, if there's any modification that happens to a signal and that's unwanted, then that is called noise. And obviously, in all cases, in all signals, we want to minimize the noise. So we want to understand what are the sources of noise. So first type of noise is called photon shot noise. This is due to the random or the quantum nature of light itself. Light photons actually arrive at you in a random way. That is, it's a little bit like raindrops falling into a bucket. You're not going to get a uniform distribution of raindrops both in time and in space. They just keep arriving. Of course, when the rain gets heavier, they arrive faster, but it's still sort of a random process. So because of that, you're going to have some noise in your image, and that noise is scene dependent because it is a function of how bright that point is in the scene. It has nothing to do with the image sensor itself. It's just nature. It's just life. And then you have readout noise. So now these photons have arrived. They've been converted into electrons very well. And now we want to read this out using the techniques that I mentioned earlier, CCD or CMOS. You want to convert these electrons into a voltage. And so during that conversion process, that circuit itself, you could have noise that is introduced. And that's before, pre-analog to digital conversion. And then during the analog to digital conversion, you're going to take this analog value and convert it into an integer value for any given precision that you're looking for on the outside. That is actually something that's being done intentionally, but yet it's modifying the signal. So that's yet another type of noise, which we'll call quantization noise. And then there are other sources of noise. For example, it turns out that even if you put your lens cap on your camera, there's no light going in, and you crank up the temperature, you could actually release photons, and that's called thermal noise or dark current noise, which is particularly a problem when you have long exposure times. And then you have fixed pattern noise, which is basically coming from the fact that no two pixels are identical when you manufacture them. There's going to be some variations. So let's look at these three sources of noise. First, let's talk about photon shot noise. So let's say we wanted to measure the number of photons coming in from a source, a point in the scene. And you can imagine, like I said before, that your pixel is a bucket, right? And you take a measurement, a first measurement, and you're given one time unit to make this measurement. And let's say you measure 3 photons. If you repeat this measurement, the second time you might get 6 photons, and a third time you might get none. And this is basically because of the variation that you have due to the random nature of the arrival of photons. This has nothing to do with the sensor itself. And so how do you model this? Well, you can model this using Poisson distribution, which is for the arrival of photons. Poisson distribution has a mean lambda. This is the value that you actually want to measure because that's the brightness of the point, the so-called brightness of the point. But you're going to get other values around the mean. So the probability that you would get the signal value k is lambda to the power of k e to the power of minus lambda divided by k factorial. This is the Poisson distribution. Here's a Poisson distribution for a mean of 1. Lambda is 1 here. And as you start increasing the mean, an interesting thing happens, which is your variance or your width also increases. And for higher mean values, you end up getting something that looks like a Gaussian right here. So the Poisson distribution has this interesting property. The variance of the signal is equal to the mean of the signal. And as I said before, it is scene dependent in the sense that the mean value that you're trying to measure is the brightness of the scene point. Okay, so that is photon noise. And now let's talk about read noise. So in the case of read noise, you're trying to convert a value, a number of electrons that you've measured into a voltage, right? In that conversion process, your circuit might introduce some noise. And that noise is often modeled as Gaussian noise or Gaussian distribution. So Gaussian distribution has a mean, mu, which is a value you're trying to measure, but the probability that you end up taking on the value x is 1 over sigma 2 pi, square root of 2 pi, e to the power minus half, x minus mu, which is the mean, divided by sigma, which is the standard deviation of the Gaussian, whole thing squared. So if you have a high quality sensor, you're going to have less spread in this distribution. If you have a low quality sensor, you're going to have a large spread in the distribution. So this very much depends on the quality of the sensor and is scene independent. So this conversion noise, read noise, has nothing to do with the actual mean value that you're trying to measure. And then, like I said, you have quantization noise. You're taking this analog voltage, converting it into a digital value, and in doing so, you're going to say your output is going to be, say, 12 bits or 14 bits or whatever it is, and therefore you're going to get one of n integer values on the outside for each pixel. And so you're taking an analog value and you're purposely converting it into a digital value. You're rounding it off in some way. And so let's say that the quantization step between two consecutive values is delta, then the variance of this noise turns out to be delta divided by 12. This tends to be pretty small for today's sensors, which are able to put out, 10 bits or 12 bits of resolution, of intensity resolution. And then we have other sources of noise. We talked about thermal noise briefly. In the case of thermal noise, like I said, if you have a lens and you put your lens cap on it, which means there's absolutely no light going into the sensor, you might still measure non-zero values at pixels. And that's because there's thermal noise, that some electrons are being ejected or released by silicon atoms because of the temperature itself. And this doesn't really happen in the case of consumer photography where the integration times are small. But in the case of astronomy, say for instance, you're looking at something really far away that's really dim and you want to expose the image for long periods of time, maybe minutes. In this case, your dark current noise could add up and could end up being a problem, which is why in applications like astronomy, often the image sensors are cooled, nitrogen cooled, kept at a certain temperature. They're very expensive systems. that use CCD and cooling in order to minimize thermal noise. And finally, we want to talk about fixed pattern noise. And this is just the result of any manufacturing process. So here on the top for comparison, we have random noise. This is just to show you what fixed pattern noise looks like. So please focus on this part right here, which is fixed pattern noise. And this comes from the fact that when you manufacture anything, no two things are identical. So you have millions of pixels, and you're going to have slight variations in the responses or the characteristics of the pixels, exactly how big the potential well is and how efficient the pixel is in terms of conversion and so on and so forth. So you get this sort of a pattern or gain associated with each pixel. Fortunately for us, we can calibrate this out. You can measure these pixels by showing it, scenes which are constant, say for instance in brightness, and then all subsequent images can be corrected for fixed pattern noise. And the last characteristic we want to talk about is dynamic range. Dynamic range is the ratio of the maximum possible photon energy you can measure. And that is because you have a pixel with a potential well. When it fills up, any photons that come in after that simply cannot be measured. And so there is an upper limit to the brightest level that you can measure. And that's Bmax. And so it's Bmax, the ratio of Bmax to Bmin, which is the smallest, the minimum detectable photon energy. So you would say, well, the minimum detectable should be as close as possible to zero. It's not the case because your image sensor is going to have some noise. And so minimum detectable means detectable above the level of noise. So Bmax by Bmin is the dynamic range. It tells you the range of brightness values that one can measure using this image sensor. And it's usually defined as 20 log Bmax by Bmin, which is expressed in decibels. So here are the dynamic ranges, very roughly speaking, of various things that we know, vision systems. The human eye is deemed to be somewhere around 1 million to 1, which would be 120 decibels. A digital camera today, roughly 4,000 to 1, which would be 72 decibels. You can compare that with the film camera, so we have surpassed film at this point. And then video is interesting because in the case of video, you're constrained in terms of what exposure time you can use, integration time. Because in video you want to have some minimum frame rate, frames per second, you're limited in terms of how long you can expose the image to light. It could be 30 milliseconds if you're doing 30 frames per second. That introduces noise because you're not measuring light long enough to get a stable measurement, and therefore the dynamic range tends to be lower, 45 to 1 in this particular case.